Today I am going to present how to determine the deflection of a beam using the unit load method. In this method, you have to apply a unit load at a point where the deflection is required. This method is applicable to beam and rigid frame where only the flexural effect is considered. In the analysis, the effect of axial force and shear forces are neglected. And you can find out what is the deflection at any point using this relation. Deflection is equal to integration 0 to L capital M small m by EI into dx, where capital M is equal to bending moment at the section due to external forces, and small m is bending moment at the section due to unit loading, and E is the modulus of elasticity, and I is the moment of inertia of the section. Then, coming to one example, determine the deflection at the free end of the overhanging beam shown in figure by unit load method. So this is overhanging beam ABC, and span AB is equal to 6 meter, and the overhanging portion BC is equal to 2 meter. And the moment of inertia of span AB is given 2I, and moment of inertia of overhanging portion is given I. And the uniform distributed load is present on the beam, that is 45 kilonewton by meter. So what you have to do? So you have to find out what is the deflection at the free end. You have to find out what is the deflection at the free end C. Here you have to find out at the point C, at the free end, what is the deflection of a beam, that you have to find out using the unit load method. So what you have to do here? In this method, you have to apply a unit load at a point where the deflection is required. So here you need the deflection at the point C. So you have to apply a unit load at the point C. Find out the deflection at the free end of the overhanging beam by applying unit load for deflection at the free end of the beam as shown in figure. So this is the beam. So first you have to find out what is the reaction by considering the external force. What is the reaction at A and B, and you have to find out the moment between the point A and B and moment between the point B and C. You have to find out the moment between A and B and between B and C due to the external force. And also you have to remove the external force and you have to apply a unit load. You have to apply a unit load at the point C, and due to that unit load, you have to find out what is the reaction at the end A and B, and you have to find out what is the moment at the section between A and B and between B and C. So first you find out what is the reaction due to external forces. First you consider the external force, that is 45 kilonewton by meter throughout the length, and due to this UDL, find out what is the reaction at the end A and what is the reaction at the end B. So you know that how to find out the reaction by taking moment about A. So you can find out what is the reaction at the support B. So first you take the moment about A, RB into 6. This is anti-clockwise. This is your anti-clockwise positive, and due to this UTL, the moment is your clockwise negative. 45 into 8 into 4. The total load is your 45 into 8, and the centroidal distance from the A is your equal to 4 meter. 45 into 8 into 4. RB into 6 minus 45 into 8 into 4 is equal to 0. Then you can find out what is the reaction at B. RB is your equal to 240 kilonewton. Then you take the summation of vertical force is equal to 0. So you know what is the reaction at A, RA, and what is the reaction at B, RB. So RA plus RB, this is upward force, is your equal to the total downward force. So the downward force is your only 45 into 8 UTL. So RA plus RB is your equal to 45 into 8. Then you can find out what is the reaction at A. RA is your equal to 45 into 8 minus 240 is equal to 120 kilonewton. So the reaction at A, you got 120 kilonewton, and reaction at B, this is 240 kilonewton. Then find out what is the moment at a distance x from the support A between A and B. What is the moment at the section? Similarly, find out what is the moment between B and C at a distance x from the pre and C, and what is the moment here, that you have to find out. So first you find out here between A and B. Find out. Taking sagging moment is positive and hugging moment is negative. Find out the expression for moment in various portions of the beam due to external force. So first to take bending moment at a distance x from the pre and C. So first to find out what is the bending moment between B and C. So take a section at a distance x from the pre and C, and what is the moment here? What is the moment here? You find out what is the moment here. The moment here is equal to mx is equal to. So what is the load here present right of this section? 45 into x by 2, and this is clockwise. The direction of the moment is here clockwise. This is rotated in clockwise direction. So the moment at the section x-axis is here equal to minus 45 into x by 2. So mx is here equal to minus 45 x square by 2. Similarly, take a section at a distance x from the support A and find out what is the moment here. So this is the reaction. The moment due to this reaction is your RA into x, and moment due to this UDL is your equal to 45 into x by 2. But this side, so this is your clockwise positive, and this is your anti-clockwise, this is negative. So here the moment at the section is equal to RA into x minus 45 into x by 2. But you know RA is equal to 120x. Mx is equal to 120x minus half into 45x square. So this is the moment at a distance x from the support A between A and B. So this is the moment. Then to find out what is the reaction due to the unit vertical load at C. You have to apply unit vertical load at C where the deflection is required. Because here you have to find out the deflection. So here you have to apply the unit vertical load, 1 kilonewton. Then by considering this load, you have to find out what is the reaction at A and what is the reaction at B. First you have to take the moment about A, that is the summation of moment at A is equal to 0. So this is reaction, and due to this reaction, what is the moment about A? RB into 6, and RB into 6 anti-clockwise positive, and due to this unit force, what is the moment about A? What is the moment about A? This is 1 into 8, minus 1 into 8. So RB into 6 minus 1 into 8 is equal to 0. So RB is equal to 8 by 6 is equal to 4 by 3 is equal to 1.333 kilonewton. So this is the reaction you got here. RB is equal to 4 by 3 kilonewton, that is equal to 1.333 kilonewton. Then you take the summation of vertical force is equal to 0. RA plus RB, this is upward direction, and the downward force is equal to 1 kilonewton. So RA plus RB is equal to 1 kilonewton. Then RA is equal to 1 minus RB, 1 minus 4 by 3 is equal to minus 1 by 3. So here you got the reaction at A is minus 1 by 3. You have to take the direction of the reaction here downward, because here you are taking the reaction upward direction. But here you got the negative value, minus 1 by 3 is equal to minus 0.333 kilonewton. You got this is the reaction. So here you have to take the direction of the reaction is your downward direction, 1 by 3 kilonewton and downward direction. Then find out what is the moment between A and B and between B and C due to the unit vertical load. Bending moment M per unit vertical load at C. Find out first what is the bending moment here between B and C at a distance x from the pre and C. So what is the moment here? So this is the load you are acting right side of this section. So 1 into x, and this is clockwise. So take this is your negative, minus 1 into x, minus x. Then find out what is the bending moment between A and B at a distance x from the support A. So what is the bending moment here? So because this is your downward direction, the reaction here. So this is anti-clockwise. So here this is also to take negative. Here this is also to take negative. Minus 1/3 into minus 1/3 into x. So this is reaction is your minus RA is your equal to minus 0.333 because this is the direction. So minus 0.333 into x. This is the moment at a distance x from the support A. Then you find out the bending moment expression of the various portion of the overhanging beam in a tabular form. So find out the bending moment expression of the entire structure, all the members in a tabular form. So first to take, this is your AB. So this is the portion AB and this is the portion BC. So for AB portion, so this is the origin, A is the origin, and for BC portion, C is the origin. And for AB portion, so what is the integration limit? Because x is equal to 0 here and x is equal to 6 here. So you have to take the integration limit here 0 to 6. Similarly for BC portion, so x is your 0 here at C and x is equal to 2 at B. So you have to take the integration limit here 0 to 2. You know what is the moment between B and C and between A and B that you have to take. So take origin for AB your A and for BC C, and take the limit, integration limit 0 to 6, and here for BC 0 to 2. Then you know capital M is the bending moment due to external force and small m is the bending moment due to the unit load. So already we have derived this moment between A and B and between B and C. So between A and B is your 120x minus 45x square by 2. Already we got here 120x minus 45x square by 2, and between B and C is your minus 45x square by 2. So here you put minus 45x square by 2. Similarly, our unit loading, so you got what is the moment between A and B and between B and C. Between A and B, the moment is your minus 0.333x, and between B and C, the moment due to unit force at C is equal to minus x. Then you know what is the moment of inertia for portion AB and moment of inertia for portion BC. So this is the value in a tabular form. Then you have to find out what is the deflection at the point C. So you know this is the formula. The vertical deflection at C, delta C is equal to 0 to L capital M small m by EI into dx. So capital M is your bending moment due to external force and small m is the bending moment due to the unit force. So you know here these are the value, bending moment value, capital M and small m. So first you have to take integration from 0 to 6 for AB portion, and for BC portion you have to take the integration from 0 to 2. So delta C is equal to integration 0 to 6 and capital M small m. So for AB portion this is capital M and this is small m. 128x minus half into 45x square into minus 0.333x dx. And here the moment of inertia are given 2i into 2i plus for this portion, for BC portion, so you have to take the integration limit is 0 to 2. Then this is the moment capital M and this is the small m. So here you put minus 22.5x square minus x dx by EI, and the moment of inertia are given I. Then you find out what is the deflection at C. So this is equal to 0 to 6 integration, then minus 20x square minus 3.7x cube into dx by EI plus 0 to 2, 22.5x cube dx by EI. Then after integration of this expression, so this is delta C is equal to 1 by EI minus 20x cube by 3 plus 3.75 x4 by 4, 0 to 6 integration plus 1 by EI 22.5 x4 by 4 and 0 to 2 integration. Then after putting this value integration limit. So finally you will get the deflection at C is equal to minus 135 by EI. So here you got the deflection is your negative value, the deflection is your upward direction. Positive, this is your downward deflection, and for negative value, this is the deflection is your upward direction. So delta C is equal to 135 by EI upward direction. So this is the deflection at C using the unit load method. Now clear that how to find out the deflection at the C using the unit load method. First you have to find out the moment of the entire structure due to the external force. Then you have to find out the moment due to the unit force where the deflection is required using this formula, and by taking the integration you will find out what is the deflection. That is the deflection at C is equal to 0 to L capital M small m by EI into dx. Then coming to another example, determine the deflection and rotation are the free end of the cantilever beam shown in figure by unit load method, given E is equal to 2 into 10 to the power 5 Newton by mm square and I is equal to 12 into 10 to the power 6 mm. EI value is given, and you have to find out what is the deflection and rotation of the free end of the cantilever beam. Cantilever beam ABC, and one load is present at point B 20 kilonewton, and another load is present at the free end C 20 kilonewton. So you have to find out what is the rotation and deflection at the free end. Here you have to find out the deflection and rotation. So what you have to do here? So for deflection you have to apply unit force, and for rotation you have to apply unit moment. For deflection you have to apply unit force at the C, and for rotation you have to apply unit moment at C. Find out the deflection and rotation of the free end of the cantilever beam. Apply unit load for deflection and the unit moment for rotation at the free end of the beam as shown in figure 2 and 3. So first to find out the bending moment for external loading. What is the external load is your present on the cantilever beam. So due to that load, first to find out what is the bending moment between A and B and between B and C. For B and C, so you have to take a section XX at a distance X from the free end C, and you have to find out what is the moment of the section. The bending moment at a distance X from the free end C between B and C, and the moment of the section is equal to mx is equal to, this is the moment, this is 20 and this is x. So this is clockwise, so mx is equal to minus 20 into x. Then take another section at a distance x from the point B between A and B, and you have to find out what is the moment here. Mx is equal to, because this is the distance is your x, so due to this force, so what is the moment here? Minus 20 into x, and due to this force, what is the moment here? Minus 20 into 2 plus x, because this length is your 2 meter and this length is your x meter. So what is the moment due to this force? Minus 20 into x plus 2, and due to this force, minus 20 into x. Minus 20 into 2 plus x minus 20x. So this is the moment between A and B and between B and C due to the external loading. Then find out what is the bending moment due to the unit vertical load at C. Due to unit vertical load at C, so find out what is the bending moment between A and B and between B and C. Here you have to find out the bending moment, and here you have to find out the bending moment. The bending moment at a distance x from the free end C between B and C is equal to mx is equal to minus 1 into x, because this is the force and this is the distance. Minus 1 into x. Mx is equal to minus 1 into x. Similarly, between A and B, bending moment at a distance x from the free end P between A and B is equal to mx is equal to, so due to this force, what is the moment here? -1 into this distance. So this is x and this is your 2 minus x plus 2 -1 into x plus 2. This is the moment due to the unit vertical load at C. Then here bending moment M2 for unit moment at C. Here you have to apply unit moment at C. Here you have to apply unit moment at C, and due to this unit moment, you have to find out what is the moment at a distance x from the C between B and C, and at a distance x from B between A and B. Here you have to find out the moment, and here you have to find out the moment due to this unit moment. So what is the moment here? What is the moment here between B and C? Because here there is no load, only the one moment. So this moment here also the same, the moment. This is equal to M. Bending moment at a distance x from the free end C between B and C is equal to mx is equal to -1, because this is the moment. Here the moment is your minus, mx is equal to -1. Similarly, what is the moment here? Bending moment at a distance x between A and B, and what is the moment here? Mx is equal to -1. So here also the bending moment is -1. Then after getting the bending moment between A and B and between B and C due to the external loading and due to the unit force and unit moment, then find out this the total expression of the bending moment for various portion of the cantilever beam in a tabular form. The bending moment expression of the various portion of the cantilever beam are tabulated below. So here you take the portion CB and BA. So this is CB portion and this is BA portion. And what is the origin of this CB portion? C. And what is the origin of the BA portion? B. Because here you are taking the x distance from the point B. So this is the origin for AB portion, and for BC portion, this is the origin. So here this is the bending moment expression of the various portion of the cantilever beam, and this is the origin, this is the limit, this is the bending moment due to the external force, this is the bending moment due to the unit force at C, this is the bending moment due to the unit moment at C, and this is the moment of inertia. Then find out what is the vertical deflection at C. Delta C is equal to 0 to L, capital M, small m1 by EI into dx. Then for this portion, BC portion I, and for AB portion 2I. So this is for AB portion 2I, and this is BC portion I. Then delta C is equal to 0 to 2, 20 x square by EI into dx plus 0 to 2, 40 plus 40x into x plus 2 by E2I into dx. Then after simplification, after taking the integration, then after putting the value of 0 to 2, so you will get what is the deflection at C. So deflection at C is equal to 53.333 by EI plus 253.3333 by EI. The total deflection at C is equal to 306.67 EI. So this is the total vertical deflection at C. Then find out the rotation at C, theta C. So for rotation at C, so here you have to take the capital M and small m2, capital M and small m2, because this is the moment due to the unit moment at C. So here you have to take, and this is the moment due to the external force. So here you have to take for rotation, you have to take capital M and small m2. So theta C is equal to 0 to L, capital M, small m2 by EI into dx. Then here you know for BC portion, this is for AB portion. This is the value you have to put here. This is for BC portion minus 20x, for small m2 is your -1. Minus 20x minus 1. Similarly here, this one, capital M, and m2 is your -1. This is capital F. This is M2. Then after putting this value, then after taking the integration of this expression, this is theta c is equal to 1 by EI 20 x square by 2 0 to 2 limit plus 1 by 2 EI 40 x square by 2 plus 40 x 0 to 2 limit. Then you have to put here this value. After putting this value, you will get the theta c is equal to 40 by EI plus 160 by 2 EI. So this is equal to 120 by EI. So this is the rotation at C. Theta c is equal to 120 by EI. This is the rotation of the free end of the cantilever wave. Now I will stop here.